Learning Commons. Oh, okay, there we go. It's being recorded. Yeah, so it will be recorded. We'll get started in a few minutes. We just want to make sure that everyone who is going to attend will attend. And yeah, my plan was kind of just going through maybe like a few questions from each topic. But if you got particular questions you want to go over, you can just send them in the chat. Otherwise, I'll just go over a couple of the topics. But yeah, we'll get started maybe in about 5 minutes. Right. You should be able to see my screen, right? Are we good?
I can see it.
So you could see the problem book and everything, right? We're good?
Yeah.
Okay, awesome. Alrighty, so we are recording. We are all good. Um, just a reminder, please fill out the attendance form that was posted again in the chat. It's super important for us to have like an accurate number of how many people show up, because that way we can get more funding for more sessions like these. So if and also if this session is helping you at all, make sure to fill out the attendance form, sorry, the feedback form at the end of the session. So this session is going to be recorded, and it's going to be on the Learning Commons website. We'll send a link for that as well, but it's on the Learning Commons website as well as the Learning Commons YouTube page. So any of the previous recordings for this class that you might have seen, you'll be able to find them in the same place. Additionally, there are also, it'll also be posted in the Discord as well, where you'll be able to see other recordings as well. All right, with that being said, let's get started. So first things first, everybody's number one question, right? What's going to be on the exam? Let's go over that. So we have a couple of different topics that we're going to be going over, right? The first topic is Gödel numbers, right? These are the ones where you make a prime factorization and you either add or subtract one from each power and you get your Gödel sequence. These are probably one of the easier questions. Next, probably one of the most important topics, regular expressions. This is probably going to be one of the biggest topics that's going to be on the test, so definitely make sure you're good with that. Grammars are also going to be another one. There's going to be a couple of different types of these. Some might just be converting a regex to a grammar. There's telescoping grammars. And this is just the type where it's like a to the n, b to the 2n, and you have links between them. These actually are not too bad. They look scary, but they're not. Then there's the actual hard grammars. These are the ones that are going to have like 5 different conditions that you have to solve for. We can go through a couple, but I'll be honest, you don't have to answer all the questions on the test. She gives way more points than you need to pass or even get 100 on. So please don't feel like you have to answer every single question. It's totally fine if you don't. So I would prioritize the stuff that's a little bit easier for you. There's probably going to be, give or take, maybe 100 points on the exam. 40 points gives you like a C. 60 points gives you like 100%. So you could definitely afford to skip the topic and you'd be okay, but would definitely focus it on regex and grammars. And finally, the last topic, automatons. Sorry if I'm a little congested, just getting over a cold. So automatons, right? These are the diagrams connecting like 2 of these nodes together via transitions. Depending on if she gets to it or not, she may include pumping lemma on the exam. That's only if on your last class before the exam, she got to it. If she did not get to it, or if you don't even know what pumping lemma is, do not worry about it. And even if you, even if you did, even if she did get to it, expect only one question on it. So I would not put as much effort into that topic. I would go over these. And these are the ones that we're going to just go over in this review session. There are videos on pumping lemma if you wanted to go over it yourself. But I just would not worry about that just because even if it is on the exam, it's only going to be one question. So these guys are the most important. Would definitely say emphasize regex, grammars, and automatons as well. And even if you just focus in on your strengths, like let's say you're super good at like regex and automatons, but maybe not so good with grammars or Gödel numbers or something, like you could still do perfectly fine. Any questions about the exam topics? Please fill out the form if you haven't already. All right, cool. We're going to go over some Gödel number questions to start with. All right, so what are Gödel numbers, right? Let's try to find a nice question to go over. Right, this is her problem book. So we're just trying to, the way honestly to go through these types of topics is if you're struggling with a specific topic, go through the problem book. Because they're all organized by their type. Now, some of these earlier ones are going to be very strange from what you've seen before, so I wouldn't worry. Focus in on the ones that are very similar to like past exams that you've seen. So that's why I'm kind of skipping through a lot of these guys. Like this is like very overkill. Yeah, these are kind of more cardinality based. Regex, where are the Gödel numbers? Okay, this is good enough. All right, so over here, right, we are calculating the pre-image of the number 6930. Okay, so when we do this under Gödel numbering, all this is saying is I'm going from the number to the Gödel. And so when we go from a number to a Gödel, we want to subtract 1 from all the powers. When we go from a Gödel to a number, we're going to add 1 to all the powers. This is the most important rule. If you know this and you know prime factorization, these are super easy. So first things first, we have to do the prime factorization. 6930. Okay. So you're looking at this big number and you're like, how do I divide this? We're ignoring the answer over here. The best way to think about it is, okay, what is an easy number that I can divide these guys into? Well, I see it ends in a 0, so I know there's like a 10 involved here. Okay, how about I start by dividing this guy into 10? Because 10, I know divides nice and evenly into 2 and 5, both of which are primes. So I'm going to circle that. All right, cool. What do we got here? Now we got 6, 9, 3, right? We got rid of the 0 at the end. Okay, well, all 3 of these guys are divisible by 3, right? So I could easily do on the side here, 6, 9, 3 divided by 3, right? And this would give me 2, 3, 1. Okay, cool. So I know it's divisible by 3. Now I get 2, 3, 1. Okay. So now it's getting a little bit trickier, but that's okay. We can rule out some other choices. We know that it's not divisible by 2. We know it's not divisible by 5. How about we go for a larger one and try to divide by 7? Okay, this divided by that is 3 minus that, 21. Okay, and that's 33. Now we're getting somewhere. So 7 and 33. All right, 33. This is a number that is divisible by 11, right? 11 and 3. Wow, look at that. We got all primes. Once you get to these prime leaves on the bottom, then you're done with your prime factorization. Now let's write this out. What does this mean? Okay, this means this number is composed of 2 to the 1 plus 3 to the 2, because there's 2 3s, plus 5 to the 1, plus 7 to the 1, plus 11 to the 1. I'm just counting how many primes there are. Now that this is in the proper order, right? Godel numbers are always going to be, they're going to be ordered numbers, right? They're going to be in the same order that the primes go. So the first position of our sequence represents the number of 2s. The second, the 3s. The third, the 5s. The 7, and continue on with 7, 11. If there was a 13, if there was 17, 19, etc. Once you get to like 19, that's like kind of the extent that it'll go to. So over here, right, we know that we have a power of a 1. Well, when we go from a number to a godel, we subtract 1 from the powers. So that becomes 1 minus 1, which is 0. Now in the 3 position, we have a 2. 2 minus 1 is 1. 5 to the 1. 1 minus 1 is 0. 7 to the 1. 1 minus 1 is 0. 1 minus 1 is 0. That means that our final godel sequence is going to be 0, 1, 0, 0, 0. Notice you always have to have these brackets. This is denoting that it is a godel sequence. And that's how we would go from a number to a godel. Okay, what if we were to do the other way around, right? The other way around is actually even easier. If let's say I were to give you a sequence as follows, right? Let's say I did 2, 1, 3, 1, 0. Okay, so we know each of these positions represents the prime numbers in order. So this is saying, right, this is the number of 2s, 3s, 5s, 7s, 11s. I could have kept going and going and going if I wanted to. I could have done 13, 19, 17, 19, etc. Okay, cool. So that means this is 2 to the what power? Well, this time I'm going from a godel sequence to a number. So I add 1. So this becomes 2 to the 2 plus 1, 3. Then I have multiplied by 3 to the 1 plus 1. That's going to give me 2. Next, I have 5 to the 3 plus 1, 4, times 7 to the 1 plus 1 is 2. Times, lastly, 11 to the 0 plus 1 is 1. Multiply this guy out and you have your number. No calculators are allowed, unfortunately. So I don't think it should be this long of a number if you were to actually calculate it. Can you leave it like that? It's a good question. I think she prefers if it's actually solved, but I'll be honest, don't waste the time in solving it when you can get points on another question. Yeah. But I mean, for something like this, if I were to go by this, I would recognize, okay, 2 to the 3, this is 8. 3 squared is 9. 5 to the 4th. Okay, I probably should not have done that big of a number. I don't think you would have this big of a number anyway. But kind of just like breaking it down into like these different pieces. And I mean, even just doing calculations on the side is fine. So you could use the back, honestly, of the paper for calculations. She does not grade the back. So like if you have to just do that for a little bit of scrap paper, because she will not give you scrap paper. So just use the back. Okay, so that's pretty much godel numbers in a nutshell. Any questions on that? There's one other thing is that they ask if there exists a godel number. The most important thing is godel numbers must be consecutive, meaning that I can't have 2 times 3 times 7. This doesn't work. What's missing? 5 is missing. Anytime you have a gap, you can't have a Gödel number, meaning that this does not exist. So that's very important in case they ever ask, hey, can this be a Gödel number? If it's not consecutive, absolutely not. And that's actually what they're asking over here. Construct an integer greater than 25 that does not have a preimage under Gödel number and explain your construction briefly. Actually, exactly what I wrote there probably would have been totally fine, right? 2 times 3 times 7. Right, this is 21 times 2. That's definitely bigger than 25 and definitely does not have a Gödel image. So yeah, that's kind of how you would do a problem like that. Okay. She used a simpler number as her answer, but honestly, anything that is not consecutive is totally fine. Okay, there was one other question that I kind of wanted to go over. This one. Okay. This one looks confusing. It's actually quite simple. So we're just going to do this really quick and then we'll go to regex. So over here, right, we know that S is equal to this sequence. And this is just a Gödel sequence of numbers we just don't know. So this refers to the number of 2s, the 3s, the 5s, the 7s, 11s, the 13s. It's just saying this is 2 to the x1. Okay, remember this is Gödel sequence to a number. So we would add 1. So that's literally what this is saying, right? And obviously the same goes for all the others. So we want to represent the preimage of the number 104 times m. So this is the number 104, its prime factorization times the prime factorization of the number m, which is represented by this. So we know what m is. So let's do 104. All right, immediately I know I know there's going to be 2, right? So I could just divide this immediately by 2, right? And for that, I would get 52, right? This guy I can divide by 2 again, right? And this would get me 2 goes in twice. 26. Okay, cool. And then 26 I know divides 13 and 2. All right, awesome. So I know that I'm left with 2, 2, 2. So that becomes 2 to the 3 times 13 to the 1. Okay. Now you're probably realizing, hey, isn't there an issue here? We're clearly missing a ton of primes. Yes, 104 on its own, keyword on its own, is not able to be in a Gödel sequence. But it's not on its own. It's being multiplied by m. And what does m have? Consecutive primes. So all we need to really do is just show that if we multiply two numbers together, right, this is saying times m. All right, so we know that it's going to be the same exact sequence, but with the extra 3 here and an extra 1 here. Because it's whatever these x1, x2, x3, etc. is with these extra exponents in there. Okay, so all I'm going to say is whatever x1 is, add 3 to it from the exponent over here. And whatever x6 is, right, this is representing 13, add an extra 1 from that exponent. Everything else is the same because there was no x2, x3, x4, etc. in my 104, but there is in my m. So all we do is we factor out the number that they give you and multiply that by its actual image there. And what are we going to get? Same thing, just add the leftovers, add the little extras in the right positions. And let's say that this had a number that was a little bit different. Let's say that we could still use this, but let's just say that we had a 17 involved there. Okay, notice that 17 is not in this. Now, because of that, we'd have to add another entry in this table, but there is no x7. So I would just write 17 I know is to the first power. So because I'd go from a number to a godel, 1 minus 1 equals 0. I would put a 0 in the 17 spot. Notice how this is a little bit differently approached because we don't have an existing number to add our numbers to. Because of that, we just know for a fact it's 0. This is a constant. It's not based on any variable. So in case the number was a little larger and they didn't have the exact same numbers there, that's what you would do in a case like this. So it would be the same answer, but just instead of this being the last one, you'd have a 0 at the end. So that's the only difference for the question, for if it was similar to that. And by the way, you do not have to prove it like how it's here. This is just to help you understand it, really. So honestly, just having this is totally fine. You only have to prove it if it does not exist. Okay, let's move on to some regex. If you have any questions, again, feel free to ask in the chat. And don't forget, please fill out the attendance form. Yeah, a lot of these questions, again, this is your problem book that has been like probably for like the last 30 years of exams. So some of the questions might look a little different. That's okay. Don't worry about the ones that look very different from like the ones that you've done on practice exams. Focus on the ones on practice exams. Here we go, regex. Cardinality counting problems. Sometimes she puts them, sometimes she doesn't. It depends. I find usually in the winter and summer, she will a little bit more. If we have time at the end, we can go over some. There is like a video on that if you wanted to kind of go over that as well. I just really want to try to focus in on like the topics that are going to be the most on the exam. Because again, if you can do godels, regex, grammar, automatons, like that's probably enough to like easily pass first of all, and probably almost to probably get 100 on it. Like you could honestly, if you get perfect on that, like you don't have to worry about anything else really. So that's why I want to really try to focus in more in with the time that we got. You know, if we had like a 6-hour review session or something, sure, let's do every problem in the book. So anyway, for a regex, right? All right, we can decipher this one to start with. So over here, right, key thing about regex, right? We have unions, and we have concatenations, and we have stars. These are the 3 main things that you need. If you got these, you can make any language you want, basically. Well, with some exceptions, but any regular language you want, put it that way. So union is saying 2 choices. I could choose an A or I could choose a B. That's saying one character. I either choose the A or I choose the B. I think of it as like a choose your own adventure. Concatenation sometimes is represented by a dot. In this case, it's just 2 parentheses next to each other. You could think of it as being multiplied. And this is saying put 2 characters next to each other. For instance, A dot A or A union B, A union B. This is saying put 1 character and then another character. So I could do something like AA, BB, AB, blah, 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 blah. And then lastly, we have star. If I have something like a star, this is saying 0 or more. A's. So I could have a string of a lambda. I could have a string of an A, A. You get the picture, as many A's as I want. Going back to this question, what is this saying? I'm guaranteed to have an A or a B in this position, an A or a B in this position, and then I can choose as many A's or B's as I want. So what is this going to look like? 2 definite characters followed by 0 or more characters. So it's a string that has at least 2 characters, basically. And what is this asking you to do? Write 8 distinct strings over alphabet A, B that first of all belong to L and then don't belong to L. Okay. So this is literally saying any strings that I want that follow this format can work. I could do AA, AB, BA, BB, AAB, ABB, BAA. I could literally do A, etc., etc., etc. if I wanted to. Keep it simple, keep it straightforward. Anything works that works for the regular expression. You could be as creative as you want. Just keep it simple. Also less writing for you anyway. All right, now 8 distinct strings over the alphabet AB that do not belong to L. Here's the trick though. 8 distinct strings. Do we have 8 distinct strings? Let's find out. So we know that this is of length 2 or more, meaning what's the opposite that doesn't belong? Length 0 or 1. That's very limited. That cardinality is very, very small. 0 is just the string lambda. 1, well, I can't just put in random letters. I have to use only A or B, meaning I only have 3 options here. So I can't do 8. I can only do 3. And that's basically what this is saying here. There's only 3 strings that we got total. And it's impossible to list more than 3 of them. So it's impossible. I mean, there are questions like this that will be impossible, and that's okay. The key here is to realize what does belong to your language and what does not belong to your language. Okay. Likewise, this is a very similar question, problem 56 over here. Let L be the language defined by this regular expression. Right? This looks a little bit more complicated, but it's okay. We could still do it. This is saying C star, so as many C's as I want, concatenated with this over here, a B or a C star. And again, with a star as many times as I want. So what are some strings that could work for this? Okay, well, first things first, notice this has a star and this is a star. I could just straight up do a lambda if I wanted to. And the reason for this is because 0 or more times for this thing, I could just say, nope, 0 more times for this thing, nope. So that's what I'm saying, keep it simple. If you could do lambdas, like why write out the whole thing? I could do something like a C, right? I could say ignore this part, just do C. I could do CC. I could do as many C's as I want, basically. But let's use the rest of this language and try to find some other stuff too. I could say ignore this part and have just a B, right? I could have a B, B, B. I could have whatever I want because again, I'm choosing B or A, C star. I could have a C, 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 right? I could choose the 1A here and then have as many C's as I want. I could do A, C, A, C, A, C, right? That's this part over here. You could do all sorts of things. But here's the thing. Remember, I could choose B or A, C star here, meaning that after this initial C star, which we're going to ignore, I have to maintain this order. that anytime I have a C star, an A needs to be in front of it, meaning that I can't have something like this, BC. This is bad because where are you getting this C from? You're saying, oh, isn't it from here? No, 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 no. This is not C. This is AC. An A has to come before the C. Again, I can do A, C, 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 as many C's as I want, but there must be an A before that. So any string that has a BC is bad. So you can make any string that you want that has BC in it, and it's bad. And that's quite literally what is being done down here, right? These are the ones that work for L, and these are the ones that don't work for L. And notice it's just a bunch of strings that have BC in it, and these are strings that don't have BC in it, right? I could do B's, but anytime I have a C, I have to have an A in between. I can have CB, that's totally fine because again, right, I could do C's beforehand if I wanted to. That's totally fine. But I can't do a B and then go straight to a C because that would mean I go right in here into this part, and that's no good. So when you're doing questions like these, find the rule. Find the general case, find what's good and what's not good. And you're trying to kind of read the fine print here. Find what can work and what can't work. And that's going to be your L and your non-L. Any questions on a question like this? Okay. All right, now we get into these types of questions. These you will always see on these practice exams, like 59 over here. This is a very, very great question because notice it has multiple parts. And because it has multiple parts in it, look at that. D, E, yeah, there's like 5 different parts to it. Guess what? You can get partial credit. Isn't that awesome? So even if you don't answer all the parts, you could get partial credit. If you understand A, but you don't understand B or C, guess what? You get points for A. Partial credit is better than no credit. Do the easy ones first. If there's an easy regex and a hard regex, do the easy one. So these are very good to go over. And if you've done practice exams, you will notice that there is usually always one of these multi-part ones in there. So definitely, get those points. So let's go through a couple of these really quick. Let L1 be exactly those strings over the alphabet A, B, C that begin with C. Okay, so what is that literally asking for? Anything I want, it just has to begin with a C. So when I do these problems, I start out with what I absolutely need. I need a C. After that point, I could have any A, B, or C that I want. And there's no rule against how many times I could have these things. The only requirement was I just needed a C. So this is literally just going to be anything I want, A or B or C star, with a C in front of it. That's it. So yeah, sometimes these can be really easy. You want to do those easy ones first. All right. Now let L2 be exactly those strings that do not begin with the C. Okay, so it's the opposite now. All right, well, we know that if we don't have a C at the beginning, that means I have to have an A or a B beforehand. Okay, then I can just choose to have an A, a B, a C star. Right, see, it's the same structure. The one thing here, though, is I could also choose to have an empty string altogether. The reason for this is because notice, this is do not begin with a C. This is the opposite of this over here. And for that reason, right, if it does not begin with C, technically, wouldn't an empty string not begin with C? So because of that, I can choose to have a string like that. So the way I like to think of these questions, because you're probably thinking, oh, I wouldn't have thought of that lambda at first. Think about your main case first, right? The most like obvious case that you can think of. That's saying, okay, I have an A or a B to start, and then anything I want. Cool. Now let me think of any exceptional cases. And these usually going to be your zeros and your ones. Length 0, meaning a lambda, or length 1, meaning an A or a B, or whatever the language is saying. These often get overlooked because in a case like this, it's covered, right? I could say ignore this and just have an A, just have a B. But in some cases, you might have to take into consideration that you might only have 0, you might have nothing at all, or you might have 1. So that's the strategy I like to do when it comes to these types of questions. So always consider your base cases in that case. All right, let L3 be exactly those strings that satisfy all of the following properties. All right, now we get into multiple properties. First symbol is B, the last symbol is B, and C occurs exactly once. Okay. Now, before you start writing out like a huge regular expression that covers like the first case, then the second case, or the third case, you could overly simplify this. So first, write down everything you need. I know I need a B as the first symbol, a B as the last symbol, right? And a C has to occur somewhere in the middle. It just has to occur once, right? Well, I know my base case here, right? At the very minimum is going to be B, C, B. This is what's absolutely required. So I'm not going to have lambdas, right? Because I need a B, C, and a B, right? That I absolutely need. But now I can choose to have things in between these B, C, Bs, right? I know this is the first and I know this is the last, but this C does not have to be exactly in the middle. So I could have anything I want here and anything I want here, right? But with one caveat, the C occurs exactly once. It's not just saying there is at least one C. If it said there was at least one C, then yeah, I could have anything, literally anything in between these guys. But because the C can only happen once and I have put the C there, I'm limited to all non-Cs, A or B star, A or B star. So for that reason, this is saying put a B, put a C, put another B, and in the middle, have any non-C characters you want. So I could have a string that looks like B, C, A, B, right? The C does not have to be perfectly in the middle. It just has to have the opportunity to be sandwiched by these guys. It's like you're making a burger, you know, you might have the patty towards the top or towards the bottom or right in the middle. You don't know. Okay, let's move on. Right, so we did C. Right, now we got D and E, right? Okay. All right, so D over here is, again, over ABC that satisfies all the following properties. The first symbol is different from a B, meaning it's a non-B. The last symbol is different from a B, and the symbol B occurs exactly twice. All right, before we start like going into this, right, we know that the first symbol and the last symbol is a non-B. Okay, so that means the first symbol is going to be an A or a C. The last symbol is going to be an A or a C. We know that for sure. We also know that the actual symbol B occurs exactly twice. So what am I going to do? I'm going to sandwich them somewhere in my regex sandwich, right? We know it occurs exactly twice. Boom, 1, 2. Meaning now I can choose to sandwich this with any optional toppings I want, but they just can't be Bs. So I could have any non-Bs here, non-Bs here, non-Bs here. So I made my base case. Now this is just saying anything extra. Right? I'm saying A or C star because we can't have a B. We've already put them in here. But I want to make sure that I can have an infinitely long regex that I want. I remember one of the most key things that the professor always says, you always want to have every single regex that is good and no regexes that are bad. So you want to go through that in your mind. Do I have, remember, if I only had this, yes, this is good, but I'm missing out on a lot of good stuff too. So that's why we always want to have these cases involved here as well. Right? Alrighty. Then lastly, we have E. Okay. So E is let L5 be exactly those strings over the alphabet where the symbol A occurs at least twice, but at most 4 times. Okay. So that means I could choose to have it. Remember, it says at least. So 2 is fine, 3 is fine, and at most 4. So 4 is fine. So that means I can have a regex that has A twice, 3 times, or 4 times. So there's a couple of ways to do this, right? I could just straight up say, okay, going back to the way I did it before, A, and surround my 2 mandatory A's with any B's or C's. B's or C's, B's or C's. And now notice I could do this now unioned with 3 A's and have B's or C's in between here. And then I can union this with 4's. But notice how long this is getting. This is getting really unnecessarily long. Yes, you can write this. This is totally fine. You can write this. But why are you going to write this when there's an easier way to do this? So the easier way to do this, right, is to kind of go through the fact that at most 4 times. Actually, wait, no, there isn't really an easier way to do this, I think. Or actually, oh yeah, there is. Okay. Yeah. So first things first, if you notice with her answer, right, she said let beta, this symbol here, equal B or C star. Now notice, every time that I had a B or C star, she just put beta. This is totally fine. You can do this, right? You can just set some character, like let X equal B or C star, and just use that. That's totally fine. I've done this before on like my exams and stuff because on some of these, you do not have the time to write out like A or B or C star, A or B or C star. So in a case like this, right, this is totally fine. So instead of writing out B or C star, I could literally just say X. I'm using X just because I cannot write Greek symbols for the life of me, except for lambda. But yeah, like that's totally fine, right? And look how quick that was. Woohoo. And then of course there's the 4 option, right? So 1, 2, 3, 4, X is in the middle. You get the picture. That's an option.
We have
But
to be, we have to be careful with the kinds of symbol we use, right?
yes, that's a great point. You want to make sure that you use symbols that cannot be mixed up with their lowercase forms. So actually, X is probably not the best option because is it a capital X? Is it a lowercase x? The world may
Yeah.
never know. So with that being said, maybe using a B, like a capital B would probably be better for that case, right? Or you can use a Greek symbol beta like she did. I just am extremely bad at writing Greek symbols. So let's just say a capital B, right? This is fine. This is like referring to it as a function, very similar to how it is in grammars. But anyway, let's do the easier way of writing this out though. Remember, we can do 2, 3, or 4 A's. Okay. Now, if I had 4 or 3, doesn't that mean I have to have 2 by default? I could factor out those 2. And the way that this would look is like this. First things first, I have my two A's. I am surrounded by non-A's. Even if I had four, right? Four A's would just be this times two, literally. Obviously, you cannot do this. This is illegal. But just thinking of it like that, right? So I can choose now at this point, leave it like this, or put another A, or put two A's. Now, this is the thing. I can't just say, oh, just do like A star or like AA star. That doesn't work because this is saying zero or more times. If this said just at least twice, then yeah, I could totally do A star. That would be totally fine. But remember, it's saying at most four times. We have to control it, meaning I can only have at most one A here and at most one A here. But I can't just leave an A here because this is saying mandatory. I have to have a choice. Take the A or don't take the A. It's as if you're going to Chipotle and they ask you, do you want sauce or do you not want sauce? I could choose A or our favorite lambda. What this is saying is, do I choose sauce or no sauce? Sauce or no sauce? I could say choose lambda, choose lambda. What am I left with? Two A's. So this is kind of like a little trick that kind of makes it a little bit easier to write because look at how quick that is compared to writing out what we had before, where it was the case of the twos, then the case of the threes, then the case of the fours, and the whole thing was like extremely long. But for this, we factor out what they all have in common and then have this as like the extras. Sometimes the lambdas could be a little confusing. So does this make sense to everybody? By the way we did it before, being extremely long, is totally fine. But you're more uh you're more apt to make a mistake with a longer regex. You might not have enough room and it wastes time. So if you can, do it easier, but a right answer is better than like having a right answer is better than having a wrong uh simplified answer. Right? You want to have the right answer regardless. So if you feel more comfortable writing out the case of the twos, then threes, and the fours, as long as it's right, you get points. There's no rule saying that you lose points if it's not like if it doesn't look good. The only way you'll lose points if it doesn't look good is if your handwriting is really bad. But my handwriting is pretty bad, and I don't think I really lost points. So just try to keep it legible, I guess. All right, so that was a long regex question. And that's like the type that you'd see on an exam, likely. So mostly just kind of switching around like the letters and everything. Switching around like what is required and what is not required. But if you understand these rules, then this is like pretty much like the gist of it. Like you can tackle any of these problems at this point. And I highly recommend you try to tackle a lot of these problems because the only way you will improve is by doing them. She tends not to have these 0 and 1 problems. If you're one of Bachman's students, he tends to have these 0 and 1 problems. So perhaps we could do one of these, I guess. Really quickly, I guess. All right. These are a little bit more confusing, but it's the same thing. It's just with binary, essentially. So let L1 be the set of those strings over alphabet 0, 1 that contains exactly 2 zeros. Okay, so just like before, right? I can have a 0 and a 0, right? That's totally fine. Surrounded by these guys, I can have any non-zeros that I want. What's the only non-zero? 1. 1 star, 1 star, 1 star. So the same way it works as the way before, right? So that's part A. Okay, part B contains at least 2 zeros. Okay. So again, we need 2 zeros minimum. Okay. I could have a 1 star here. Actually, wait, it contains 2 zeros, right? I could have more than 2 zeros if I wanted to. So instead of just saying 1 star, now at this point, I can use my whole alphabet, but I just have to guarantee these two at least. So I could say 0 or 1 star, 0 or 1 star, 0 or 1 star. Because for this, because it's at least 2 zeros, I can choose to have more zeros. I just have to guarantee that these guys actually happen, because if these guys never happen, I'm left with my 2 zeros, and that's fine. Okay. And then lastly, part C, contain at most 2 zeros, right? So think about it. How many zeros can I have? I can have 2, I can have 1, I can have 0. So this is going to be a case like what we did before. We can write them out, right? We could write out each of these cases, or take into consideration, what do all of them have in common? They have a 0 in them, right? The smallest number. So because of this, right, I can choose to have a lambda, right? I could choose that as a case of just completely zeros. And that would just be a case with ones, right? But I need to have, so that's like literally my base case in a sense, having just like literally 1 star. But I need to be able to take into account an optional 1 or 2. So what do I do for this? Well, I could have 0 or lambda. And then I can choose to have another 0 or lambda. And surround these guys with 1 stars. And the reason for this is because if I choose lambda on both of these guys, what am I left with? Just 1 stars. And that's totally fine. Before, I had to have zeros. So that's why it was 0, not 0 or lambda. For this, we just factored out the fact that there were 0. The smallest number of zeros is literally 0 zeros. So all of these guys happen to have a case in which there are no zeros at all. We just have the optional parameter of having 0 or no 0 in each of these. And yeah, 0 is different than a lambda, right? These are literally alphabet symbols. Your alphabet, instead of being AB, is 0, 1. So it functions the same way. It just sometimes could be a little bit more confusing. I just wanted to do one of these really quick. She doesn't usually put these on, but in case she does, just don't get confused on it. All right, good to go over grammars now, or any other regex questions you guys have? Yeah, a lot of these kind of get to like the same as you're going along with it. You guys asked about cardinality, right? This is kind of cardinality with regex expressions, right? We can go quickly over this a little bit. So here, right, we have ourselves, where did I put my pencil? Oh, here we go. All right, we have a regular expression, A or C star. What's going on here? I could choose A or C 0 or more times. So we want to state the cardinality of the, oh wait, I'm sorry. Oh, I did not, okay. Oh, we have to actually get the, the regex first. I'm sorry, kind of skipped ahead there. Okay, I'm like, okay, I thought they were just asking for the cardinality of just that like A or C star. That's what I was confused about. Let's actually derive this stuff by itself. It's good practice. And I actually see there's another trick over here, right? Is this crazy stuff? This is not too bad. So we're going to go over it. So we have L1, L2, L3. L1 be exactly those strings that have exactly two B's. Okay, well, we did this one already, right? Put your two B's here and A or C, A or C, A or C, right? So that's totally fine. Then we want to say now, write the regular language that represents the language L1 star. Okay, when I have a star here, it works the same way as thinking of A star, right? This is literally just saying take your language and put a star around it. I'm not kidding. That's literally what you do. And all that's just saying is I could take this whole thing and I could have it multiple times. So I could have the string go multiple times. And that's really all that star is saying. So you could star a language just like you star a symbol. Okay, now we go on to L2. What is L2? Exactly those strings where the number of B's is even. Ooh, this is a good one. Even and odd is definitely going to be a major thing, right? The key to remember, 2n is even, 2n plus 1 is odd. And all this means is that the number of characters have to be a multiple of 2 to be even. How do you make that odd? Well, take any even number and just add 1 to it. So now you know how to find an even number and an odd number. To find the number of B's that are even, right, you always want to make sure that you have that ratio of 2n for B's, right? So every single time that I call a B, I have to call 2 of them together. And this is actually not too bad to write out, right? All I'm going to just say is BB, right? I can have whatever I want in between here. That's totally fine. A or C star, A or C star. I don't care what I got in between. I just need to have 2 B's. And now I star this. So every single time that I call 2 B's, I am guaranteed, every time I call this, I'm guaranteed to have an even number of B's. It's always going to be 2, 4, 6, 8, 10, etc., etc. But the problem is, what if I choose not to call this at all? Okay, you have a lambda. That's fine, but we're also missing one other key case here as an edge case, right? What if you just want A's and C's? So all I got to do is just take into account A or C at the end over here. It could be at the beginning or the end. The order doesn't really matter, but this is just saying, okay, I can choose to have an even number of B's, but if I don't want any B's at all, I don't want to call this thing. I just want A's or C's. That's where this guy comes in. So that one was just a little bit more, and you could see over here, right? We have this part here, A or C star B, A or C star B, A or C star B, the whole thing starred. She put the A or C star at the end. The order literally does not matter. This is just kind of a backup to ensure you have A's and C's in case you don't call that function. So that's how we do one like that. Now, what do you think it would be if it was odd? Well, 2n plus 1. So with something like this, right, I'd always make sure at the end here that I'd have a b, right? So this would make sure that I have 2n plus the 1. And now this whole thing would get starred as well, right? Because we want to make sure that this constantly, actually no, because then this could happen twice. We don't want to star that, right? In a case like this, we want to make sure we have a b at the end, because if we had a star here, I could just straight up be like, ignore this, BB, haha, it's even. So in a case like this, I would just straight up have something like this, right? And just say B or lambda. Have a B around this whole thing, or like a lambda at the end, just to take into account that I could choose to have like an empty string or not. That's if it was odd, by the way. The question was asking even, but just so you can kind of see that literally, I'm just kind of adding a B at the end and calling it a day from that. Now that we move on from that, let's take a look at D. What is L3? Okay. L3 is equal to, wow, we got a lot of stuff here. Let's break it down. L2, this is the complement sign, right? You probably have seen before in like 220, something like that. You can write it like this too. And this is just saying L2 without L1 star, unioned with a lambda. Okay, so let's take a look. What was L2 again? This guy, right? So this is just saying, give me everything in here without anything from here. So what do they both have in common? This part. This could literally be factored out on both of them if I wanted to. Okay. What am I left with? A or C star. Okay, so this whole thing here, that's L2 without anything from L1, is literally just this part. This is your leftover. This is A or C star. Unions with the lambda. Now, the lambda is included in this already because of the star. So if I did a union with a lambda, it doesn't mean anything because I can generate an empty set, a lambda, just from this guy. So with that being said, the answer would just be A or C star. Now, if I did not have that star, then my answer would have been A or C or lambda. So just kind of a key thing there. And that's why this guy down here was just A or C star. So remember, the backslash is the complement. It's saying this without this. So just kind of break it down. And then of course, union, you just add whatever they have on this side. But lambda is already in A or C star, so we don't have to change that. Right, now we go into cardinality, right? So what is the set of L1? We have a couple of different cases here. Finite, infinite countable, and infinite uncountable. Okay, so let's go through those guys. Finite, you can count it, right? You know exactly how many it is. If I have A or C, one character here, one character here. Cardinalities 2. That's an example of finite. You can have infinite countable or infinite uncountable. Infinite countable, it's an infinite number, so technically it sounds like you shouldn't be able to count it, but it has a predictable pattern to it, meaning that if I have something like the natural numbers, right? Those are your numbers 1, 2, 3, 4, 5, 6, 7, etc., etc., etc. I can choose to keep going and going and going and going, and I always know how to get to the next number, right? I constantly know +1, +1, +1, +1. If I know the pattern and it's predictable, that means that it's infinite and countable. There's another way of thinking of it if you can map it to the natural numbers as well, which was the example I gave, right? Meaning that if I could have mapping, let's say like, let's say mapping every natural number to its square or something, right? So like 1 square, 2 square, 3 squared, 4 squared, etc. That is countable because I can map it directly to the numbers, the natural numbers. I can easily predict what the next one is going to be. Uncountable, on the other hand, is things that are all over the place. The common thing to think about is this is rational,
real numbers, right? Real numbers. I'm sorry, that's rational numbers. Yeah, for real numbers. And the reason for this is because a real number isn't like a rational number, right? Rational numbers are like 1/2, right? 1/4, etc. And you might have gone over it in class, but there's this thing called the think of the triangulation proof or something. It's like the one that looks like a staircase, and that's just saying that you can literally travel through every rational number in like a zigzag pattern like this. And all that really proves is that because you can predict what the next one is going to be, they are countable. So rational numbers are countable, real numbers are not. And this makes sense because think of real numbers. I could have 0.1, I could have 0.001, I could 0.000000001. How do I know which is the next one? So that's kind of the difference with those guys. Going back to the question itself, right? We want to do the cardinality of these three guys. So we have over here, right? We have stars. The second I see a star, I know for a fact that I'm going to be infinite. And the reason for this is because a star is 0 or more times. Is it happening 1 time, 2 times, 1,000,000 times, infinite times? We don't know. We know immediately all three of these guys, 1, 2, 3, and 4, they have stars involved. They're going to immediately be infinite, right? Now, the key here is to think, are they infinite countable or infinite uncountable? Now, given that with these guys, right, that they're a little bit all over the place, right? We can't necessarily control with the star how many times that we're going to be having it, right? And because of that, I could choose to have 1 time, 2 times, 3 times, 1,000,000 times if I want to. In a question like part A, right? A or C star B, A or C star B, A or C star. There isn't necessarily any rhyme or reason to calculating these guys. So, oh, wait, it is countable. Oh, wait, I'm overthinking this. It's because it's a regular language. Okay, so never mind. I'm overthinking this. Okay, with real numbers, right? It's all over the place. There is no rhyme or reason. But notice there's a keyword here, regular. I know that sounds like it should be obvious, but what regular is saying is that I can create this nice formula to generate all the possible outcomes. I have a formula. If I have a formula, I can count them. It doesn't seem like I should be able to count them, but there is a formula. Just like with rational numbers, there's the whole triangulation proof. It sounds like it should be infinite and uncountable, but you have that whole zigzag pattern. It's a method. It's an algorithm to count them. What do we got here? A regular expression. It's an algorithm to count them. So anytime that you have a regular expression, it's always going to be countable. The key to know is it finite or infinite? And it's super easy to find that out because infinite, star. So this is actually a really, really easy question with the cardinality problems. If you are asked to find a regular expression with a star, it's always going to be infinite countable. A regex without the star is always going to be finite. And finite is always countable because you can literally count it if it's a finite amount. So super easy way of going over it. Yeah, I was just overthinking that question. But with regular languages, it's very easy to know for that case. So it's always going to be infinite and countable. Or if it was something like literally the example I had up here, right? A or C, I know it's always going to be 1 plus 1 is 2, finite, and therefore countable. So that's kind of just a little bit of cardinality.
Any questions, comments, concerns? All right, with that being said, let us move on to grammars. All right, we got about 45 minutes left, I think. So I think we should be able to make it through grammars and automatons. By the way, since we've kind of hit a midway point, if you can fill out the attendance, not attendance form. I'm hoping you all filled out the attendance form already. If you could fill out the feedback form. And chat. Oh, Zan beat me to it. So if you could just fill out that feedback form if you get the chance, in case you have to head out early, totally get it. You got your Saturday to hopefully relax, study a bit. So I appreciate all the feedback, by the way. So if you have any questions, you're free to join the Discord, honestly. There's the Discord for the chat for the class. A lot of the resources are posted there. Yeah, absolutely. I'm there as well if you want to like ping me with questions, or you could just put them in the chat because there's always someone there to kind of answer questions as well. Oh no, the file crashed. Oh, okay, we're good. All right, let's do grammars and automatons, and then at that point, we are good. So I'm gonna go over one grammar of each topic, right? So going back to like the main topics there that I just erased before, that's really helpful. We had the three main topics of grammars.
Yeah.
Those were the easier grammars, the harder grammars, and the telescoping grammars. We're going to do one of each, and yeah. So grammars aren't too bad. Let's go over one that's a little bit more involved with these guys than these guys. That way we could see kind of what's going on. Yeah, this is a good one to do. So sometimes you're asked to find a language based on a regex like this, and the answer is like literally here. Like this is, obviously I know the answer is here, but the answer is like literally given to you in the problem. You're literally just converting between these two guys over here. So anyway, let me just move this over so I have a little bit more room to write. Just put this into the sketch pad. Yeah, this sometimes is a little bit a lot to write out, let's just put it that way. But you can kind of still do it in everything in the space that she provides. You just have to learn to write kind of tiny. I am not very good at doing that. That's why I am going to be writing the sketch pad. In case I end up writing extremely big, I can just make things smaller. Righty. Thank goodness for iPads, right? So what are we doing here? Well, the first thing we do is we break these down into pieces. Anytime I see a star, it's a piece. It's going to be its own function. So this is a function.
this is a function. This is a function. And a star here is a function. Right? Immediately, stars are going to be functions. Sometimes also, it's helpful to break things down based on unions. So this is a function, and this is a function. Because think about it, what am I doing? I'm literally breaking this down into choice A or choice B. Let me label these guys out. This is A, this is B. I'm going to skip C because, again, lowercase c, capital C. What's the difference? If you don't know, don't write it. D, E, F, never, ever, ever use G because G means grammar. So we go to H. Those are the two main rules. Don't use G or anything else that is a capital letter that represents something. And don't use capitals that are similar to lower cases. Otherwise, use any letter you want.
Letter. Or any letter you want.
Sorry, if you could just mute yourself. Okay, so whenever we do this, we want to start out with writing grammar is equal to what we call VEPs. Nice, easy way to remember it. So this is the set of variables. Sigma is always your alphabet. P is your production set, aka just your rules. And S is your starting point. We always start out at S. S is this entire string you can think of. What is S composed of? Well, look at your outermost functions. I broke it down into A and B. So, oh, sorry, A union B, right? This is A or B. That's why we break them down into functions, because instead of actually writing this whole thing out, this thing is function A. Instead of writing out all of this on the right, that's just function B. Now I can choose to define what these guys are saying. What is A? Well, A is composed of two other functions, D, E. Notice they are concatenated. There is nothing between them, meaning that everything on D is concatenated, is put right next to anything with E. It's like you're printing two words together. Okay, and then B. What is B? B is comprised of this whole thing. We have ourselves a D. Notice a lowercase d. Now we're getting into letters. This is shown with function f. We have ourselves two lowercase d's. And then we have function h. So notice anytime we have the stars, we just bundle them right into a function. Oh, I'm so sorry. I made a mistake here. Yes, this is supposed to be A line B. So in regex, you write a union. In grammars, you write a line. So these are exactly the same. This is just how to write it in regex versus grammar. Concatenation still works the same. We just put it next to each other. Thanks for catching that. All right, so now that we did all the outer functions, right, let's do the inner functions. Let's start with the left, D. I could choose BA or BAA. BA or BAA. Notice though, I have a star. So I have to add one more thing here. I have to make it recursive. Now I go over this all the time, two different ways, because there are two different ways you can write this. Choose the way that's easier for you. Both are correct. I could have a recursive case separate, then a lambda, or I could write this as or BAD, BAAD, lambda. Let's go over why both these ways work. If I were to have this first case, right, this is saying if, sorry, if I were to have this first case, right, I have DD. My first D, I could choose one of these guys, whichever one I want. My second D, I'll recurse again. My first D, I'll choose one of my cases. The second D, I'll recurse again. Choose the DD. My third case, my first D here, I can choose one. Let's just say I chose the second one this time. Doesn't really matter. My second D. All right, at this point, it's getting very long. Let's stop here. Lambda. Lambda's my stop sign. Okay, with that being said, that's one way to work. Otherwise, I choose here. BAD is my first case. The D allows me to do BAAD. Call it again, BAD. Now at this point, if I want to end, this D just becomes a lambda. Both of these ways work. They're totally fine. I did both on this one, but in the future, we'll just pick one and stick with it. Again, pick whichever one makes more sense to you. Either way is totally fine. All right, now we go to E, right? We finished D. EB or EEB, star means have a recursive case. Okay, moving on to F. F is just A or B star. A, oops, or B, FF lambda. And then finally H, right? H is just A, right? So I'm going to just write this as the second case, right? AH lambda, because otherwise I'd have to write that out as AHH lambda. So it's a little bit more writing. So I'm just going to simplify that as that case. Okay, and with that being said, we are done. The last step, though, is, again, this was our production set. So production set is equal to. We wanted to find what each of these things is. Variables. Which ones did we use? S, A, B, D, E, F, H. Sigma is equal to A, B, C. Wait, no. A, B, D, E. And then we already defined our production set. So always make sure that you include your variables and your sigma on each one. And this is what that problem will look like finished. Questions? Isn't this kind of telescoping? Well, telescoping is a type of grammar, so yes. But let's do a telescoping problem and see why it's different. Telescoping's slightly harder only because it's a little confusing at first. But once you do some problems, then it becomes pretty intuitive. What on earth is that? Oh, it's just a pumping lemma layout. I'm like, I've never seen that before. Yeah, if you haven't done pumping lemma yet, it's like this proof to determine if things are regular or context free. Okay, where are the telescoping problems? Great, you know what? There's not one there. I'm just gonna make one up myself. I'm not in the mood to really look through that right now. All right, telescoping. Telescoping is a little bit different because it involves a string that looks similar to this. AN B2N, right? Now, of course, there's going to be much more than that, right? I might have A3J plus 1, BJ plus 2. Actually, let's make that an I instead. Let's switch the order around. I plus 2, C, I plus 1, A 2J plus 1, C 2H, and D 3H. Okay, and let's just do one more in the middle. Okay. This is a telescoping problem. And notice, we're not in a regex world anymore. We have exponents. Now this exponent establishes links between characters. There's a link between the N's. There's a link between the I's and the J's and the H's. And this poor little guy is all by himself. What do links mean? Well, let's go to the simplest example here at the beginning. A to the N, B to the 2N. For every A, there are 2 B's. That's all it's saying. Meaning that for here, for every 3 A's, there's going to be 2 A's on this side. And notice there's also a +1 and a +1. And we'll get into that after. But these are just saying the relationship between these characters, basically. When we're making a grammar for these guys, every link is going to be its own function. So this S, right, this is still going to be our S. This is still going to be our whole starting point, our entire sentence. But here's the difference. I'm going to make each of these guys their own function, right? A, B, skipping C, D, E, and F. Even this little guy on his own, he gets his own function because despite there not being another link for this, it still is a recursive function because it's happening 2 times whatever the number L is. Let's write this out now. So we actually already know what our VEPS is going to be, right? V is equal to S A B D E F sigma, that is a horrible sigma, is equal to A, B, C, and D, right? These are just our lowercase letters. Production set is equal to our starting point, and these are going to be our rules. So what is this equal to? Well, let's think of it the same way that we did the last time. What is S comprised of? A, B, D. Okay, cool. Let's unpack them one at a time. First things first, A. What's A? Well, first of all, A is A to the N, B to the 2N. So what am I going to do? I'm going to do A, B, B, just like how I did before. Where's our recursive case going to go? In the middle this time. Why? Because this is saying for 1A on the left, 2B's on the right. So I'm always going to have to go outwards. So every time I call this, I'm going to have AA, BB. So 1A on the left, 2B's on the right. And notice how it telescopes outwards. That's why it's called telescoping, guys. So that's what we're essentially doing here. Now, this is our base case, but I'm just going to add an n+1 here to show that we also need our, I'm sorry, this is our recursive case, right? This is the case that's going to recurse over the function, the relationship a to the n, b to the 2n, based on the exponent. But now, given that I wrote a little +1 here, what about that little extra one? Well, that is just going to be our second case. We could think of this as like a star. Remember, I can do a star, I could have 0 times. If I do a 0 times and I have something like this, a star b, then this just says 0 a's and a single b. That's my stopping condition. Well, if n was 0, I still have this +1. So that little leftover a goes as my end case. Very similar to the problem we did last, right? Where this case was a lambda instead. This time it's just an a because of that. If that +1 was not there, then this would be a lambda. Okay. So that was A. While we're doing some easier ones, let's do D. Because B is going to have a recursive, it's going to go inwards. So let's do D while we're here to really lock in the topic. C to the 2H, D to the 3H. Okay. For 2 C's on the left, there are 3 D's on the right. That's what these coefficients are telling me, right? Every time I recurse over the function. I put my function in the middle, my recursive case. So this is able to go outward. So each time I call this, 2 C's on the left, 3 D's on the right. All right, now I need my end case. Notice, these guys don't have a +1 on them. So because of that, right, there's not going to be anything. I'm just going to have a lambda. So notice this is a case that has a plus leftovers. This one does not. Lambda. Right. Everyone good with that before we go to the one that's going to be having another function inside of it? Right? B. All right, start with the outer part. We have a to the 3j plus 1, a to the 2j plus 1. Okay, so that means for every 3 a's on the left, I'm going to have 2 a's on the right, given the coefficients. Okay, have my recursive case in the middle, b. This allows me to go through it for as many j's as there are. Now it's going to be a little different though. I have a +1 on both sides, but I also have something in between here. So instead of last time when I stopped, because again, this was my end, at that point, I just put a lambda in there, right? This time it's going to be a little different. I'm going to have my leftovers. 1a on the left, 1a on the right. But what goes in between is function e. Because that's what's in between these guys. It's not just a lambda this time, or just the plus a from the leftovers. We're going to have our next function that we're going to. So our base case is going to actually recurse on its own function. Now we can define function e. E is saying b to the I plus 2, c to the I plus 1. All right, so if that's saying 1b for 1c, call my recursive case e in between there. And now, what are my leftovers? I have 2 b's, 1 c. Where am I going? What's inside function f? It's like one of those, the Russian dolls, like you could open them up and there's another layer inside of them. There's another layer inside of them. That's literally what you're doing. You're unpeeling the layers until we get to function f. Notice function f's all by his lonesome. It's just d to the 2l. So all that's saying is 2 d's. Notice he does not have a pair. So there won't be anything on the right. It's just going to be my function. So dd f. Just like how we've done these cases before in the past. Okay, now for my second part, right? There are no leftovers. If there was a +1, I'd have like a d there, but there are none. There is nowhere we're going either. We don't have anything in between here. This is the end. So to mark the end, lambda. Again, if this was like a +1, I would just have a d there and call it a day. This marks the end of the question. Question for A, if we had a to the n plus 1, b to the 2n plus 1, would it be a, let's see, that was a to the n plus 1, b to the 2n plus 1. That would be, okay, so that would be 1a there, 2 b's there, a, and then that would be a, b. Okay, so for your answer, you had 2 a's there. The reason that it would be a, b, and not AA is because this has a +1, this has a +1. So these are your 2 leftovers at the end. And we're assuming that this was from function A, so we don't have anything in between. So I don't have to worry about any other cases in between these guys. Yeah, so that would be if this was 2n plus 1. Could she ask us to make an automaton for a telescoping one? No. The reason for that is actually kind of related to pumping lemma. And I'm assuming that you guys haven't really covered it, so I'm going to just try to make it as simple as possible. But you have 2 types of languages, right? Regular and grammars. Regular languages can be written with regex, right? Kind of self-explanatory. These also can be written as an automaton. Regex and automatons are interchangeable, meaning I can translate them very easily. grammars are not always regular. They can be, but the second I have links in them, that means it's no longer regular. Think about it. How could I ensure that there's exactly 3 A's and 2 A's always on a recursive call? Wouldn't make any sense because a star can't control that. Even if I were to say A, and then AA, right? And I did something like this. This is saying all the links of all these 3 A's are on the left and all these 2 A's, it's always going to be in this order, right? We want all the 3 A's on the left and all the 2 A's on the right. I can't control this. I'm not recursing from here. I'm putting a star around this whole thing. So this whole thing is going. So I'm having 3 A's, 2 A's, 3 A's, 2 A's. That's not the same as this. With that being said, that's kind of literally what you're going to be doing when you're proving pumping lemma, by the way. Obviously more in like a rigid proof, but because of that, this telescoping will never be in an automaton. So if you have a regex, it can easily be an automaton. Grammars are only in automaton format if they are regular. The second you see links, not regular. So yeah, we'll go into an automata question for the next one. Links, these guys, same exponent. Notice how I linked them together. The N's are together, the J's are together, the H's are together, the I's are together. The L has no one, so it's all by its lonesome. So if links, it's not regular, meaning I can't make an automaton. Non-telescoping grammars will, non-telescoping grammars don't have links. So the one we did before, oh, wow, there was one right here this whole time. Wow, okay. Yeah, these are the telescoping things, right? Literally the same kind of format, right? These guys are not regular. Yeah, they're kind of in the pumping lemma section in case you want to practice some, because it's very closely related to pumping lemma. But if you have a regular expression that you're converting to a grammar, it's regular. You're starting out with a regular expression, so it is regular. So I can do an automaton for this. So telescoping literally just means that it has links. That's all it means. Because you telescope based on the links. Good with this? Other questions? So remember, we went through those 2 types of grammars. Regular grammars and telescoping, aka not regular. Only regulars can be made into automatons. The non-regulars can't. With that being said, let's get into automatons as our last topic of the day. I think we'll have time for a quick 1 or 2. Right. Let's do 194 really quick. This is a smaller one. And then we'll do one where we convert a grammar into, like a regular grammar into an automaton. And I think that'll be all for today. Okay. So we have the case that all A's come before any B's. And the number of A's is at least 2, but the number of B's is at least 3. Okay, cool. So that means any A that I have has to come before any B. So it's not like I have to, interchange them or anything. So we're essentially going to break this down into 2 sections. The thing is going to be recorded. We'll have the link probably emailed to you guys. It'll also be in the Discord. So don't worry about it. It should probably be up, I'm hoping by tomorrow-ish. I'll try to get it out quick for you guys. It's the Learning Commons that's posting it, so it's not really my video, it's going to be their video. So anyway, we're breaking this down into all the A's and then all the B's. The A's has to be at least 2. So remember, I have to guarantee 2, but I can have more than 2. So how did we do that before? A, and then I could have anything I want, anything I want, anything I want. And then B's, same thing, but now it's 3's. B, B, B. In between of these guys is anything I want. All we got to do is just turn this into an automaton now, right? So remember, with automatons, we have our starting point with the little arrow coming out of it, right? And what we're going to do is we're going to say that, oh, actually, this is simpler than I thought because it's only A's and B's. So there are no C's, there are no anything else. And all the A's have to come before any B's. So instead of just having literally anything I want in between of these guys, it's literally just going to look like this. A star. B, B star. 2 mandatory A's. I can't put anything in between them because, again, I need my 2 mandatory A's, and then I also need my looping part, the part that's going to have A star. Then I have for my B's B, and then B star. It's a loop. And all the A's have to be to the left, all the B's have to be to the right. Okay, cool. So let's just write this in automaton format. The links are just going to be as follows. An A transition brings me to the next state. Another A transition brings me to the next state. Next, here, when we do automaton loops, right, we can do this 2 different ways. Because it's only 1 character we're looping, I'm only going to do just an A loop like this, right? It doesn't matter to go to actually make its own state at that point. Because otherwise it would be a little bit more confusing. And we try to do that only really for ones that are going to be multiple characters. For instance, if I had like A, B star, right, I'd have something that looks like this. A and then B, right? Kind of looping back and forth. Or something along these lines as well. I could do A, B, right? And then I could have a transition looping back for a lambda. And remember, the star allows me to go 0 times, so I can choose to skip it. Lambda. We're going to do one like this in a little bit. So, but just, we were doing a simpler one right now, so let's just kind of keep it simple. Simple and straightforward, right? So we got this over here. Cool. Now we have the B part, right? I'm slowly running out of room, so I'm curving this. So I honestly am not very good with writing them out in clean ways. Because of that, my handwriting is kind of big. So just pardon the curve as I'm going around. Right? B, and then another B. These are my 3 B's. Now I'm going to have a loop for a B. Now at this point I can end. So I can do the little target at the end. And that target is going to just mark the end of this. If I had a little bit more room, it would not have been curved. It would have looked more, yeah, it would have looked more like this, basically. But as long as it just works the way it doesn't really matter what it looks like. It just really matters that you get from point A to point B effectively. Okay. So with that being said, that's how we would draw it. Also, the right 5 distinct string parts that belong in L, we kind of did this before, right? It's any number of A's that have at least 2, followed by any number of B's that are at least 3, right? That's kind of literally what we got over here, right? You could just really write out anything you want. Alrighty, so with that being said, let's get a harder one to do. You know what? I'm just gonna make my own again. Just want to make sure, we're getting through all the problems. So I'm gonna make a regex and we're gonna just do the make a regex and then we're gonna just do the automaton for that. Okay, so A or B star, A or C, B. This whole thing can have its own loop too. C, A or BC concatenated with A star or BB. Okay, that's good enough. And let's put a union here. All right, this is fine. So first things first, we're going to identify the outermost part, just like how we would do for grammar, right? I know this is its own path and this is its own path, right? We're not really able to write out functions in the term of identifying this is A and this is B, like how we are with grammars, but I can identify this as a function, as this is a path and this is a path. So when I start out, I know I have one path here and one path here. Now, one important thing here is the first one over here has a star and the second one does not. So with that being said, anytime that I have a star, right, I want to make my first path into a lambda transition. Why a lambda transition? Because remember, I'm choosing path A or path B. There are no loops to bring me back. If this second thing had a loop that brought me all the way back here, right? I could accidentally go into this one, right? It's as if you're trying to get into like a subway train, right? And you're able to go backwards on the turnstile. Turnstiles are made so you can only go one way, which is what this lambda is doing. So because of this, when I have this inevitable loop, right, I do all the stuff, blah, 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 and I loop. I go back here. I don't go here because if I went back to my starting point, I can go this way again. So this allows me to not have a chance to go back through the turnstile and go down another path. It's like you're getting 2 bus fares or 2 train fares for free. You shouldn't be able to do that. So with that being said, anytime that I have a star on one of these paths, I'm putting a lambda transition here. This does not require one because it does not have a star, right? This part here, we're literally just going to be doing CA or BC concatenated with A star or BB, right? So with that being said, I don't really need a star. I don't need like a path, like 2 paths there. I mean, I don't need to have, sorry, a lambda transition there. But anyway, let's go back to the first part. I have a lambda, and now I'm free to go on to my next part, because anytime I loop back, I'll always loop into this state over here, not this state. So what do I have first, A or B star? So this means that I can choose to do an A or a B as many times as I want. And the easiest way to draw this out is a loop. And I can do A, comma, B. Comma is the way of showing an OR with an automaton. Or I could do just two paths just like this, if it's for more than one character. But because it's only one character, I can just write this out nice and simply. Okay, then this gets concatenated with A or C, B. So now at this point, because there's two paths, I'm going to do an A, or I could choose to do a C and then a B, right? And both of these guys are going to actually lead me to the same state, to the end, right? Or I could choose to loop back. So I'm going to just revise this a little bit and show that I could get to this last state either way, right? I could do an A or I could do nothing at all. But I need to keep in mind the star. So from this end state, this is where I'm going to get into that lambda loop from before. I can go backwards on a lambda, and this lets me go through the whole thing all over again. Or I could go forwards as a lambda, and it lets me skip it entirely. So that is this half over here. Now we're good to start the right half. So the right half, I have two choices here. I could do CA or BC. Okay, so that allows me to do two paths, not just one path. So I could do C, A, or I could do B, C. But remember, it's one choice. So I either go down this path or this path, but both lead me to the same place. This same place allows me to do this part. And I'm going to actually add a star here just to kind of spice things up a little bit. Because I have a star on this whole path, I need a lambda here. Now, this is not as crucial as before because there's no other path here, right? These are one-way transitions. But if this had a star on it too, I would have had lambda transition going back, meaning that I could have ended up going backwards to the very beginning and getting a free bus fare down the other way. So because of that, I usually just always do a lambda transition anytime that I have myself a star on a big part like this, right? Because when you have like a big part like this that has a star, not just a single character, I know I'm going to have one of these pesky lambda transitions that could result in me going in the wrong place. So anyway, with that being said, right, I have my two choices. I could do A star, right, or I could do a BB. So for that matter, right, I'm going to say I can do A star, right? So I can have a loop here. Or I could do BB. Okay, so in this case, right, I could go down B, B. Now, this whole thing can get repeated, right? So actually, let me not have the A star here because this is making it look like I could do A star then BB. Because it's a union, I want to make it its own path. So I'm going to honestly just have another lambda transition here. Notice, star, I could use a lambda transition. I could use a lambda transition anytime I want. But anytime I have a star that I don't want to accidentally loop back on, I'm just going to have it look like this. Now again, this marks the end. But because I have this star, right, to make it a little bit less complicated, I'm just going to have them both end at the same place. Anytime I don't know, I don't have a symbol to put, but I want to bring it to the next transition, I just have a lambda, right? It's just like another subway transition. Now here, remember, this whole thing is what I'm looping on. So I have one lambda going forwards, one lambda going backwards. And this is my ending state. So this would be the automaton for this question. So I kind of wanted to show you like with the lambdas, how it can get a little crazy at times, but how the lambda is a solution to allow yourself not to accidentally loop back on the same thing. It allows you to keep the same order. You can use as many as you want. It's better to be safe than sorry. Use more than you need if you really want to be safe. For instance, look, I used one here, I used one here, I used one here. Technically, I really didn't need the one over here because there was no loop going backwards, but I'm just doing it to be on the safe side. For the C and B part at the beginning, you said it's not required to do the lambda transition there, but you could still have it there, right? This one is required. This one is required because notice, this is going into a star loop. If I did not have that lambda transition here, notice my loop going backwards ends here. If I didn't have that lambda, it would end here instead. And that allows me to go down this path instead. But or, which is the union, is exclusively or. I can only choose one. It's like you go to a buffet and you're only allowed one dessert, but you go back to the back of the line and you get a second dessert. This lambda is like a security guard that says, hey, move along, you got your dessert, go leave. So yes, you can have multiple ending states. That's fine. This is what we call a non-deterministic automaton, meaning I could take multiple paths. Deterministic means that you take one path and it leads you to the end. On more complicated things like this, you're probably not going to really have one path. But if you wanted to do this with one ending state, you could. I'll show you how to do that one. I'm literally just going to have an ending state over here and have one extra transition here and here to bring me to the end. So if you wanted to have one transition, you can do it that way. I just didn't because it didn't really look as nice, to be honest, but it just kind of shows you can go down this path or this path. Honestly, it really depends. As far as I know, I'm pretty sure she's okay with multiple ending states because it technically is correct. If you want to be on the safe side, you can. There really is no reason that you can't. This is still right. Right? Whether you have your two ending states here or one ending state, it's honestly okay. But if you want to be on the safe side, by all means, go for it. Honestly, it's better to be safe than sorry anyway. But now you know how to make both of them. Oh, her solutions in the problem book only have one final state. Yeah, I mean, a lot of her solutions, okay, there are multiple ways of writing automatons, just like there are multiple ways of writing grammars. You probably noticed my solutions might be different than hers. That's fine. What matters is you get to the answer. Regex is a little bit more rigid, but with grammars and automatons, you can be very creative with them. Best way to check your work on these guys, honestly, trace through it. Try to see if you can pretend to be that person trying to get cake at the buffet. If you can go backwards and go down this path and get a second dessert, you got a problem. Yeah, I mean, you could have more than one accepting state. That's honestly fine. It's just, I think, more because um, a lot of her problems in the problem book only had one accepting state. I think it's more of just like organization. Like, this kind of shows you that they are all in one state, one finishing state, I guess. I guess it kind of makes it a little bit more neat in that way. Um, there's some of these automatons that literally there's like no way to connect them. Like it's like you have like even this kind of looks a little bit of a stretch, you know. To be honest, there's probably if I did this like with like a software or something, like how she does it in the problem book, it would have been way more organized. But yeah, you can do multiple states, point of the story. But if you would rather do one, that's also totally fine. I know in Bachlin's class is a little bit different. He'll actually ask you to make either like a DFA or NFA. And that's honestly different. It's a little bit different, right? But for her class, either way works. What matters, can you get to point A from point A to point B? So, right. With that being said, this would be the end of the session. If you guys have any other questions, please let me know. Otherwise, please fill out the feedback form. We'll stay here for another 2 minutes in case any other questions come in and just to give you some time for the feedback form. Yeah, this will also be uploaded to the